We're going to be talking about series, which are the sum of a sequence. And that's the big gist of this chapter, is the idea that the sum of a sequence is a series, which means that if I take the series 1, 4, 7, 10, and so forth, that's a sequence. A series, this is a sequence. A series is if I add them up, 1 plus 4 plus 7 plus 10, etc. An infinite series is one where I add an infinite number of terms, whereas a partial series is, we call this a partial sum. And this is going to be getting into the weeds of the whole thing, but you really need to kind of get the sense that whereas we first had a sequence which had n values, which I could say n was 1, 2, 3, 4, 5, it's the position, and n is referred to as a position. T of n were the values. So maybe in this sequence, T of n's are 1, 4, 7, 10. Next one would be 13. We now have a third term that we call S of n. We use a capital letter S. And what S's are partial sums. So S sub 1 is just the first term. But S sub 2 is the first term plus the second term, which would be 5. S sub 3 would be the first term plus the second term plus the new term. That would be 12. Then S sub 4 would be adding the fourth term, which would be 20, plus 10 would be 22. And then we would add the fifth term to get to the next one, which would give me 35. So pretty much what we're saying here is that S sub 1 is 1, S sub 2 is S sub 1 plus, is T of 1 plus T of 2. S sub 3 is T of 1 plus T of 2 plus T of 3. S sub 4 is T of 1 plus T of 2 plus T of 3 plus T of 4, and so on. So the S's are the sequences of partial sums. I should just say S sub 1 is T of 1. Another way to think about it, if S sub 1 is T of 1, this can be defined recursively, which means that S sub 2 is equal to the first sum plus the second term. S sub 3 is equal to the second sum plus the third term. S sub 4 would be equal to the third sum plus the new term, the fourth term, and so on. So this is what's defined and denoted as a series. A series is a sequence of partial sums. Or put very innately, a series is the sum of a sequence. It's just adding up all the terms of a sequence. So I'm going to try to give you some value behind why series can be important. And some of this isn't going to come into play for much later. For instance, from the last chapter, we had the exponential function e to the x. And what it turns out that we can actually use series to approximate this. I know that e sub 7 is approximately equal to 1 plus 7 plus 7 squared over 2 plus 7 cubed over 6 plus 7 to the 4th over 24 plus 7 to the 5th over 120. And that actually turns into an equality if I keep this pattern going on to infinity. This is what's called an infinite sum. And it's an infinite sum where the thing that I'm adding is actually getting smaller and smaller, which is allowing the decimal value to approach and become equal to what this is. So this is just an example. Don't worry about memorizing that or anything. But this is where we are actually going to have the ability to approximate some of these functions like e to the x. E to the 7th is what's called a transcendental function. It's very difficult to attain an approximated value for it. So what your calculator actually does is it does not do e to the 7th. It actually adds up all of these only so far as to how many decimal places it needs, and then it stops. Okay, so that's what a series is, and it's an infinite sum, and you kind of really need to nail that in your head to get the idea that a series, or an infinite sum, a series is just a sum. Okay, so it also becomes very silly, very silly to write a series now in terms of just a number of terms. So one way to write a series is just to list off the first 3 terms. And as you're going to learn in later math classes, you actually need 6 terms to establish the pattern. But for now, we only need 3 terms to establish whether it's arithmetic or geometric. This particular sequence here, 1/2, 1/4, 1/8, is geometric. It's geometric with an R value of 1/2. And I could keep this going. I could actually add up 1/16, 1/32. But let's say I wanted to keep going, and let's say I wanted to stop at 1/1024. I don't want to have to write this out every time I'm communicating to somebody that this is the series I'm looking at. What I want to do is I want to have a better way to do that. So this is what's called sigma notation. Notation is just a way to write things. And to convert to sigma notation, you first need to find the formula for the sequence. And we'll call this specifically sigma notation for a series. So to first find the sigma notation for a series, we need to find the formula for the sequence. This is a geometric sequence up above with an R value equal to 1/2, a T of 1 equal to 1/2, and that means that the formula for a geometric series, the general geometric one, is T of n is equal to T of 1 times R raised to the n minus 1 power. For this particular sequence, it would be 1/2 times 1/2 raised to the n minus 1. And for reasons of simplifying algebraically, I can make this 1/2 times 1/2 to the n times 1/2 to the negative 1. And when you multiply 1/2 to the 1 times 1/2 to the negative 1, those are reciprocals. Those would cancel. So the simplified formula for this is 1/2 to the nth power, or better yet, 1 to the n over 2 to the n, which is just 1 over 2 to the n. All in all, we're saying that every term here, in position 1, you have 1 over 2 to the first power. In position 2, you have 1 over 2 to the second power. In position 3, you have 1 over 2 to the third power. That's just getting down to the sequence. You also could have just done the sequence of the denominator and realized that that was 2 to the nth power. The numerator is holding constant at 1. So that's step 1, is to find the formula for the sequence. The second step is to place the formula, and I should say place the simplified formula after the sigma. Well, what the heck is a sigma? A sigma is a capital Greek letter that looks sort of like a broken E. You may have seen this before, broken hourglass, but it looks like this. And you're going to have to get some practice drawing this. So I'm going to place the formula after that. Sigma to me looks like something that's gobbling things up, and it means the sum of all the 1 over 2 to the n's. Step C is to define the variable that is changing. So in this case, we have the sum of all the 1 over 2 to the n's, but I'm going to define the variable down here. I'm going to put n equals. Okay. Step 4 is to decide the n value of the first term. Well, that's easy. The first term was 1/2. So since the first term, I'm going to write that here, the first term was 1/2. So that's 1 to the 1/2, which is 1 to the 2, or 1 over 2 to the first power. So that's an n value of 1. So I'm now going to write this sigma, the sum from all the n equal, or starting with an n equal to 1. I'm going to say that very specifically, of all the 1 over 2 to the n's. And finally, we're going to decide the n value of the final term. And the final term up above, if you want to scroll up, you can see in it, the final term was 1 over 1024, which is the same thing as 1 over 2 to the 10th. So the final n value is an n equal to 10. And so now I'm going to put the completed sigma, the sum, starting with an n equal to 1 and going all the way up to 10 of 1 over 2 to the n. This is a fully realized sigma notation. That is a sigma that tells the sequence. You can put parentheses around the sequence formula, and it tells what variable we're changing. We're starting with n equals 1. And this is saying, start with n equals 1 and add up all 1 over 2 to the n's, changing n by 1 at a time, which means that this is 1 over 2 to the 1 plus 1 over 2 to the second plus 1 over 2 to the third, all the way up until the top, which is 1 over 2 to the 10th. So you start with an n equals 1 and you end with an n equals 10. So that is sigma notation in a nutshell. Now let's do some examples of this. Starting with, let's take this sequence, 9 plus 10 plus 11 all the way up to plus 100. And we are going to convert that to sigma. So first things first, what type of sequence is it? And let's get the formula down. So this is an arithmetic sequence with a common difference of 1 and a t of 1 of 9. So the formula we've studied for an arithmetic sequence is t of n equals t of 1 plus n minus 1 times the common difference. And we want to simplify that formula. So this is going to be n plus 8. Then we're going to take that and we're going to put this after the sigma, the sum from n equals of n plus 8. I'm going to put this in parentheses just to make sure that that is seen as a single expression. Since we called 9 t of 1, we're going to say that we're going to start with n equals 1. And we're going to end with n equals, well, it can't be n equals 100. This is not the 100th term. What it is if I plug in 100 equals n plus 8, I get n equals 92. It's the 92nd term. 9 was the first term. This is a 1, 2, 3. This would go all the way up and become the 92nd term. So again, I set that value equal to the formula to solve for the n. But also, if you want to keep things very simple, you could have said, well, this would also work. Maybe these are just n values, the sum of all the n's, and I'm starting with an n value of 9, and I'm ending with an n value of 100. This also works. There are going to be many examples in your answer key where you see more than one solution, or book's version and your version. As long as what you have is correct, then you're okay. I'm also going to start the calculator program, and we'll see if we can get that going in time. But you can plug sigmas into your calculator to kind of verify what they're equal to and check yourself. Okay, next example is, let's take a sigma, the sum from n equals 7 to 98 of n plus 2, and we're going to write out the terms. So I'm going to go from the sigma back to something else. So this means to start with 7, so we're going to plug in 7 plus 2. Then we're going to add the next one, 8 plus 2. Then 9 plus 2. And we're not going to do the whole thing. We're going to put a little dot, dot, dot in the middle and skip all the way to 98 plus 2. And if I simplify this, I get 9 plus 10 plus 11 it's actually just the same sequence we did right up above, which is just, again, another way to express it. Now, your book is going to ask you to kind of write these out, and if I flip over to what your homework is going to look like, it's going to ask in the first several questions to write a series in expanded form. We're going to add to that, do not add. Do not add them, just write it out. All you need to do is write out the values. You don't need to add them. It wants you to write out the values. And then the second bit is to write using sigma notation, which was what we've been doing. So it's sort of going backwards and saying, now can you write a sigma notation version of these sequences? It looks harder than it is. Remember, just follow the steps. Let me give you another one. Let's do write the sigma of 2 plus 5 plus 8 plus 11 and 56 is the last one. So typically the hard part is going to be actually determining what the n value is of 56, because the n value of 2 is 1, the n value of 5 is 2, and then 3, and then 4, and so on. We don't know what this is, but we can figure that out because we've been doing this the entire chapter. We're just going to figure out the sequence formula for this. I know it has a common difference of 3 and a t of 1 of 2. So my formula is t of n is equal to t of 1 plus n minus 1 times the common difference. Don't forget to simplify that. I get 2 plus 3n minus 3, or 3n minus 1. That's the sequence formula. To figure out what n value is goes with it, we're just going to set it equal to 56. 3n minus 1 equals 56. Add 1 and divide by 3, and I get n is equal to 19. So there are 19 terms there. Now we're going to set up my sigma, the sum from n equals 1 to 19. I get to start with an n equals 1 because I specifically called the number 2 t of 1. I could have called it anything, any value, but I'm going to call it t of 1 because that's the easiest of all the 3n minus 1s, because that's the formula, and that's it. That's a way to take a sequence and make it into a sigma notation. Now that I've got the calculator up, I want to show you in your calculator that if you go to the calculator part and go into the menu, you can find where some of these different tools are. Well, one of the tools that I think it might not be in your menu, but it's definitely in the templates. So I'm going to back out of that and hit the templates button that's right next to the number 9. You're going to see a bunch of these, and here's one dead smack middle that looks like what we've been doing. This is just a way to actually have the calculator add up all these things. So if I wanted to come up with a numerical value for what 2 plus 5 plus 8 plus 11 all the way to 56 is, I could actually just type in n equals 1 to 19 of all the 3n minus 1s, and press enter, and it tells me that the sum is 551. So your calculator does have the capability to do infinite sums. For your curiosity, or for your information, this one next to it is not one we actually do n-bar-buff math at all, but that's an infinite product. It's not an infinite sum. Okay. Final example is, let's do a sigma notation for 1/3 minus 2/5 plus 4/7 minus 8/9 plus 16/11, and so forth. Okay, a couple of things with this. There is no ending value. That's going to become crucial because when we write our sigma, the upper limit is going to be an infinity. It is possible to have an infinite sum, and we'll be getting more to that in 11.6. But for now, I want you to be able to see, can you see what the pattern is doing? One of the things you can see is that the numerator is operating at a different pattern than the denominator. Let's start with the denominator because that's actually a little bit easier. The denominator's pattern is 3, 5, 7, 9, 11. That is an arithmetic sequence with a common difference of 2 and a t of 1 of 3. And so the denominator's formula would be t of n is equal to t of 1 plus n minus 1 times 2. which one would simplify to 3n, or 2n plus 1. That's the denominator's formula. Now, let's look at the numerators. You could say that the numerator is 1, 2, 4, 8, 16, but it is actually 1, negative 2, 4, negative 8, positive 16. The only way to get them alternating between positive and negative is to have it be a geometric series with an r value that is negative. This would be an r of negative 2 and a t of 1 of 1. So its formula, t of n, is equal to t of 1 times r raised to the n minus 1. So negative 2 to the n minus 1 becomes the formula for the numerator. We don't need to have that 1 in there, so we'll just put negative 2 to the n minus 1. In any case, this is now pretty easy. I'm just going to take the numerator formula, negative 2 to the n minus 1. I'm going to put it over the denominator formula. We're going to do a sigma, starting with an n of 1, because I picked that here and here, that I'm starting with an n value of 1, and that's the easiest way to do it. But there is no ending value because I'm going to infinity, which is also nice because I'm just going to put a little infinity symbol on top. This is obviously something your calculator cannot handle, and we'll be dealing more with what that means in the coming days.